Hi there. We're going to continue our work on set theory. We're going to be looking in this particular part of the lesson at Venn diagrams. We'll also look at sample spaces and two-way tables. So starting with Venn diagrams, what are they? Are they related to set theory, and how do I interpret them? This should look familiar to you based on what we talked about with set theory. We have set P and set Q that are listed. Set P has 5 elements, set Q has 6. We've got a universal set. The first number in the set is 0, and these are consecutive whole numbers that go up to 12. Make a Venn diagram to represent the relationship between the sets. So our Venn diagram is going to have a box that is the universal set. Inside the box are 2 overlapping ovals or circles. Set P is the circle on the left. Set Q is the circle on the right. The overlap area is any members that are both in sets P and set Q. So let's start with that. Are there any numbers in both sets? Yep, the number 2 and the number 3. Now let's fill out the oval that represents set P. If 2 and 3 are already listed, we need to account for 5, 6, and 7. So there is a visual representation of set P. Now set Q, 2 and 3 are already listed. We need 1, 8, 9, and 10. And now we want to show any numbers that are also in the universal set, but not members of P and Q. So that would be the numbers 0, 4, 11, and 12. And the typical questions we could ask would look like things you've already seen. P union Q, P intersect Q, the complement of P, and then that last one we'll talk about. P union Q, first of all, is all of the numbers that are in both ovals. And notice that when we list P union Q, we don't list the numbers 2 and 3 twice. Now we have P intersect Q, and that's the 2 and the 3 that are in the overlap area. How about the complement of set P? All numbers that are outside of set P, but part of the universal set. I typically list these numbers in order, starting with 0, and then 1, 4, 8, 9, 10, 11, and 12. Now this last one is interesting. We are looking for a complement. And remember, complement is numbers outside of a certain set. So we're looking for numbers that are outside of P union Q. And the numbers 0, 4, 11, and 12 are in that set. So that's how Venn diagrams and set theories are connected. Here's a problem that if we are skilled at making Venn diagrams, we can probably solve this one easier with a Venn diagram. A survey of 80 students found that 42 of them are wearing red and 34 are wearing green. So we're looking at red and green. 27 of them are wearing neither red nor green. So I'm picturing a universal set like a rectangle with 2 overlapping circles, one with red, one with green. And there's certain students who aren't wearing either red or green, but we're asked to find the students who are wearing both red and green. So here's my Venn diagram that we'll be filling out. And when we're done, it's the numbers in the overlap that will answer this question. So first thing we know is that 80 students were surveyed. We also know that 42 of them were wearing red, but the problem with that is I don't know how many of those 42 were also wearing green. So I'm going to hold off on writing that number. I know that 34 of them are wearing green, but again, I don't know how many were also wearing red. I'm going to hold off on that. But the 27 of them who were not wearing red or green go down here in the corner. So how many students are represented in these ovals? That's going to be 80 minus 27, or 53. So 53 students of the 80 were either wearing red or green or some combination of red and green. So how about if I take the 34 of them that are wearing green and subtract that away from 53? That gives me 19 who were not wearing green. So that would go in this area of the red oval. Now, if I know that 42 were wearing red, but 19 of those 42 were not also wearing green, that tells me 23 students were wearing both red and green. And how many students were wearing just green but not red? Well, that'll be the number wearing green, 34, minus the 23, or 11. Now, is there a way to check that our Venn diagram is correct? Sure. Let's add those four numbers that we see in the four regions of the Venn diagram together and make sure they equal 80. They do. So that tells me I have confidence in my diagram, and 23 students are wearing both red and green. So that's a little bit with Venn diagrams. Let's move on to sample space, related to probability, also related to set theory. Because a sample space is the set of all possible outcomes of a given event. And with probability, we're always thinking about events, right? All right, so we're asked to find the sample space of each of these three events. Let's start with rolling a die. Well, if I have to come up with a set, I want to use my curly brackets. And inside of the sets are all of the elements that could possibly result from rolling a die. So we have 1, 2, 3, 4, 5, and 6. And this is going to feel familiar because you did this, some work with probability back in the middle grades, okay? All right, now what about tossing 3 coins? Well, if I was tossing 1 coin, I could get either a head or a tail, right? Tossing 3 coins, to list the sample space, I want to start with my curly bracket. And what if I got all heads? Well, there's one way that can happen. What if I got 2 heads and a tail? There's 3 ways that can happen. What if I got 2 tails and a head? And the last element that's possible is all tails. So now that I have this sample space, notice made up of 8 elements. These elements are not numbers. These elements are combinations of coin outcomes. I could now ask probability questions based on the sample space. So helpful to write out the sample space. It'll help me solve probability problems. All right, number 3, let's roll a die and toss a coin. Well, there's 2 possible outcomes for tossing a coin. There's 6 possible outcomes for rolling a die. So 6 times 2 is 12. I believe there's going to be 12 elements in my sample space for this event. So I might get heads and 1, heads 2, heads 3, all the way up to heads 6, right? That's one possible outcome. I might get tails with 1, tails and 2, tails and 3. And notice I have 12 elements in this sample space. So that's how we deal with sample spaces. Now we're going to jump to two-way tables because also related to set theory. Here's a context that is pretty accessible. 24 students in a class were surveyed if they played a musical instrument and if they play a sport. So some of the responses are listed here. 6 students were told play both a musical instrument and a sport. 3 students play neither a musical instrument nor a sport. 14 students in total play a sport. Okay, well, how many students in total play an instrument? How many students in total play an instrument but don't play a sport, right? So these are the kinds of questions we can ask. So we're going to start with our two-way table, which looks like this. Along the top, let's put plays a sport, doesn't play a sport. Along the left-hand side, let's do plays an instrument, doesn't play an instrument. We know that 24 students have been surveyed. So the total that's going to be represented in this two-way table is 24. 6 of them play both a musical instrument and a sport, so you know where the 6 goes. 3 students play neither a musical instrument nor a sport, so 3 goes in this corner. We know that 14 students in total play a sport. So how many students play a sport but don't play an instrument? That would be 8, because 6 plus 8 is 14, right? Now the question is how many students don't play a sport but do play an instrument? That I can't get automatically until I look at the total number of students that don't play a sport. Now, that wasn't given in the context, but I can figure it out from the table. Because if 14 students play a sport and 24 students were surveyed, that means 10 don't play a sport. Oh, I guess what I did first was I added across the 8 plus 11, 8 plus 3 to get 11. So 11 don't play an instrument. Okay, fine. If 11 don't play an instrument, then 13 students in total do play an instrument. And from here, I can figure out how many students play an instrument but don't play a sport, right? That would be 7. 6 plus 7 to give me 13. And the 7 plus 3 equals 10 is another way of checking that my two-way table is correct. So now I could ask a lot of probability questions based on this two-way table.